Okay, so first of all, let me thank you as the organizers for the opportunity to speak here. Actually, this will be a talk in the mathematics. So this kind of survey talk, so I apologize for the two experts here, but I thought that moduli people might be interested in something which is not moduli, but related to in the Hodge theory. Okay, so I will talk about recent progress. All right, so first of all, I have to define what loci are. So suppose you are in a situation maybe you start, and I will take the simplest possible setting. So you start with a smooth conductive moduli. That's a smooth buffer of S, and S is corresponding to the C. This is my setting, and you can think that X is the final space, and this is your universal familiar space. Okay. Then Hodge theory is interested in the Hodge structure of the fibers of those morphisms. This morphism is smooth proper, which means that the fiber is a proper smooth algebraic quantity. So its cohomology has a Hodge structure, which is of weight 2I is 200I. So what is the Hodge locus associated to this morphism? This would be a subset of the base of the morphism. And by definition, this is a set of points where there's the complex analytics. So you take and you always denote the identification of the algebraic quantity C, and it just defines set theoretically. So the set of points in the base so that when we look at the cohomology of the fiber, the context, so also think of it as being a complex compact k-denominator. Then you can take its atomic cohomology, so usual singular cohomology with coefficient Q. So this state is the Q Hodge structure, is the basic fact of Hodge theory. And you want to consider several points where the Hodge structure here is simpler than at other points, and this means exactly that these are more Hodge classes here. And exceptional Hodge classes. So I remind you that the Hodge class, if you look at the cohomology in degree 2I, will be a hypermodal class which is in HII. And by exceptional, I mean that if you look at the nearby fibers, then at that point you have more classes than in the nearby fibers. Okay, so it's just a subset of Xi. Yeah. Actually, I will need a better version of this. And this will be an important thing in the entire talk, is that it's better to consider, let me write it this way, that I apply it, where I look at the tensor here, because from the point of view of Hodge theory, it's not very natural to consider only the Hodge structure, but all the Hodge structures tensorially generated by that one. So, and this means that you're not only looking at Hodge classes in this cohomology, but at Hodge classes in all the tensor power of that thing, and maybe with its dual. Okay, so what I want to talk about is this locus, which is given for free in some sense, and of course you can generalize. You don't need to stop we find the definition. Okay. So maybe I want to start, because you are not experts in Hodge theory, by giving some example. So let's start with a very simple example. Well, actually not so simple, but let's look at for S, I will take 18, your preferred moduli space of basically y by dimension G. And for the family, I will take the unit of so 1. So again, you have to put some level structures so that this thing exists, but that's okay. So let's see the universe. And then you would like to understand what this means. So remember that you've been invited from the point of view of Hodge theory, and actually from any point of view, it's to be described like it's H1. So you are looking just at weight 1 Hodge structure, very simple object. And so I will not describe the full Hodge locus. This can be done, but will not do it. But what is for sure is that the same content, for instance, the set of points here, which corresponds to a real variety that splits non-trivially as product. So it contains the set, let me maybe GK, the set of A, F, and G, let's say, that depending values to AS is isogynous to some real values of function K, yes. G and C, and here K is some integer 1 and okay. So you see at least that this locus contains some geometric information. Now I want also to emphasize that it will also contain some arithmetic information. So another example of subset of this Hodge locus would be just a set of staples. So this means that you have exceptional endomorphism in your variety, and this is essentially a variety in nature. It cannot exist just by looking at the geometry of the variety. All right. So that's one example. The general result dating from the 16th is that look at this locus. Actually, this is the counted agreement. Of irreducible algebraic varieties. AG, and maybe I will have the time at the end of the talk to talk a little bit about what happens when you are interested really on morphism defined over a number field. And here everything is defined over Q, and actually those varieties are defined over Q bar. So this is kind of surprising, and I will explain soon why, because Hodge theory is by essence not an algebraic theory. It's complex analytic. And
yeah, that's what the first Hodge locus to be fine. The irreducible components are also irreducible components of the bigger Hodge locus?
Not necessarily, it can be embedded in.
So that's really fact. So there's
okay. I'm going to turn on what? The problem there. One down.
and if it doesn't work, keep press that button, then it fits. And it doesn't
work a lot. All right, so this is the typical example, which is kind of simple because you are working with weights. So I'm working with weight one. So let me give a second example, which is very quick. Let's consider the following situation, which is also coming from moduli theory, or other parameter spaces. I consider the universal family of smooth cycle surface of dimension n and W t in n plus 1. So this is contained. So the parameter space for hypersurfaces of liquidity in n plus 1 is just this projective space. Then there is the discriminant locus corresponding to the non-smooth hypersurfaces. I remove it and I get this UND. Okay? And over UND I have the universal family. So the point here parameterizes such an hypersurface. Okay? Universal. Okay, let's start with a very simple and very classical case, which is the case n equal to 3. So you are just looking at surfaces in T3. Okay? And let's assume that the degree is at least 4. Then okay, it's difficult to describe this full Hodge locus, but at least it contains a weight-studied object, which is what is called the natural access locus NFD. So what is it? This is a set of surfaces no surfaces in P3 such that the typical so we have the reflected map from P3, of course, to see of the surface is not an iso. So a classical result of Goethe tells you that the giant smooth surface in P3 does Picard, which is the same as the one of P3. So this is a collection of exceptional surfaces, those ones.
F tensor or F?
Here it's really H2. So I don't need the tensor. Okay, so what is the result of Miller's? So this was stated by another in 1880, I think, around, and proven by Lefschetz in 1920, is that this locus has, in the case of wave 1, and indeed is also regarded the union of elements and bias of unity. Now, this theory developed a lot, so there's a famous result of Klingler and Hodge. Says that actually you can give bounds from the dimension of those things. Maybe each electrical component y of this reference locus satisfied okay, so first of all, the codimension in U2D of such a y, well, you get an easy upper bound, which is just H20 of the surface, which in the integration what is it so? Well, what is the general condition for having a Hodge? You have to be in H11 and Hodge. But being in H11 just means that when you integrate a 0 form, a 2-0 form on lambda, this is 0. This last has to be a class. So we get exactly H20 condition. So this gives you this upper bound, and these are the giant components. What is much more difficult is that actually here you have a lower bound, which is d minus 3. And what Green and Bazin prove additionally is that they were able to characterize those minimum components. That's what I mentioned anymore. So there are the families, family of cities such that Z contains a line. Okay. And of course, this line gives you the additional class and the additional guy in the car. Then, not only the similarity, but also the characterization. All right, so this one, we have to try to do you see? You might.
So in Bruno, in this case, what do you have in the complement of NLD? So you, that is one example.
I don't want to do that. I will need description in groups or easy.
Well, I mean, that's the one.
This one?
No.
Okay, I think I will use only 2 because I don't want to. Sorry, I'm not using any more of platform. So now, of course, when you are discounting for the union, I should have mentioned before raising, in this situation, This is a countable union, and it's very easy to see that actually it's dense. You have anything dense in EG. So here again, you know that there is a countable union, and you can ask, okay, I have a countable union, what is the distribution of those components inside my modular space G? And this was answered in the 80s. So what is the result? The result is the following. Let's go and look at Gilberto, Harris, Harris, and Lambda. And then there is a better result by Mark Lane that tells you that actually the union of the John components codimension of expected codimension in each to 0. Thanks. So let's see, that's identity was proven by Gilberto, Harris, and Lambda, and then Margaret had a nice argument proving that this is actually MHD contents. So those ones I said that are the ones of the expected codimension. So let me call them the general components. And otherwise, I would call them exceptional if the codimension is smaller. You see that you have a very rich geometry. And then looking at this Harris conjecture that there should be only finitely many exceptional components, not of the expected codimension. Finitely many exceptional components. And then actually what not is proof this. This is around the 90s. This is false. So she was able to exhibit an infinite family of components which are exceptional. And then she asked the question, what is the task closure? Is it task closure? Is it darkness? Is the dark closure of the union exceptional component equal to the ability? Fine. Okay, so you see what was known for n is equal to 2, and you see that even there are a lot of unknown. And basically, for n larger than 2, and if you look at the Hodge locus of this family, and basically nothing was known before 95. And I will explain now the first big step in progressing in our understanding of the Hodge locus. Okay, so the moral of those examples is that you have a few features that you can recognize. First of all, it's purely Hodge, it's purely set theoretic locus. This Hodge locus defined purely set theoretically. Actually, in those examples, it has the structure of the cardinal union of inequalities, which is kind of surprising. And in the cases that I described, it is actually dense. All right, so let's go back now from the example to the general situation. And let's try to explain those features. Actually, they in 56 noticed that the Hodge conjecture implies that the Hodge locus of S tensor is countable union of what's part. So I think there is a good reason why what happens in this example should occur. And the reason is the following. If you believe in the Hodge conjecture, any Hodge class in your fiber corresponds to an exceptional algebraic cycles. Now, algebraic cycles have the nice properties that they glue together due to the existence of Hilbert schemes. And so this means that those Hodge locus actually correspond to families of algebraic cycles appearing over sub-varieties of the base. And so this is the justification. So that's the first point. And now the second idea is that when you do Hodge theory, maybe actually this is a little bit obscuring what happens keeping the geometry in the background. Maybe you should generalize and forget that your objects come from such a morphism. So you replace. So actually, what I was considering in this was the variation obtained by pushing forward in the derived sense local system on X. So I will replace this variation of Hodge structure by any general variation, by any variation of Z variation of Hodge structure on S. So now I need one thing maybe I will here. So what is such a thing? Such a thing is first of all a local system corresponding. Let me write an example of our situation. Right. Okay. Second, once you have this local system, you can look at the corresponding holomorphic flat vector bundle. Actually, this is an algebraic vector bundle. F and node with connection. So in our case, this is R, F, R, and node with the and connection. And now Hodge theory tells you that actually this algebraic vector bundle is stricter. And this is the Hodge equation. And here it comes from the stupid equation in this part. And now there is a polarization that I will not describe, which is crucial for all this business, which is the pairing of BZ with itself to the trivial local system. And then in this situation, you can still define the Hodge locus exactly the same way. Let's do that.
In the abelian example and the hypersurface example, do you actually get new things here?
No, I mean, this is just so the previous examples are the geometric case of that situation. But of course, okay, are you asking, are there not new examples? Yeah, this is an excellent question. A priori there are, but actually, we don't know so much. But the point is, in some sense, what I want to explain now is that basically all the progress in terms of questions in the last 15 years come from the fact that you forget that, and you will think only about Hodge theory. Because as we will see, we can interpret Hodge loci in purely theoretical terms, and then situation becomes much better. Maybe to your surprise, but it's a fact. Okay, so then in this situation, you can still define Hodge locus in exactly the same way. All right. So what is the first main result of the loci? Well, this is a famous result of Stephanie Beckner. Taken from 95 is that this Hodge locus is always a countable union, whether V comes from geometry or not. Only the countable union of closed reducible advanced varieties of and so the varieties, I would call them the special varieties. Of S form. So it's kind of remarkable. Each time you have such a morphism for E, you get this collection of reducible algebraic varieties in the base just coming from Hodge. Okay. Now, of course, the main question in this talk is to try to understand the distribution of those varieties. What can we say? What is the distribution of the special variety?
Do we also know that, like, if everything is defined to a Q1, then also the loci are?
This is not known because I will explain at the end of what is known about that. All right, so in particular, now if you look at the universal family of hypersurfaces in Pn+1 of the Ts, then you have this. And this is certainly not when using the fact that you have explicitly hypersurfaces. This result is pure Hodge. Okay, so I will come back in a moment how we see that nowadays. All right, so now, okay, so let me state maybe the theorem that you can remember from that talk. Theorem 0, at least, which is the motivation for the rest of the talk. That let's go back to the situation of the universal hypersurfaces. So if n is larger than 3 and t is at least 5, and then t is not 4, 5. Then actually, the Hodge locus of the smooth hypersurfaces of the BD in Pn+1 for the primitive probability in middle dimension in part. Okay, so we know this is the countable union of algebraic varieties. So an algebraic variety can be of dimension 0 if it's the point, or of positive dimension. So now I will keep only the positive dimensional components, which are easier to touch because there is some geometry in the background. So the idea being that isolated point in this Hodge locus, they should appear coming from IP other than geometry. Okay, so I keep so this is the union of the positive dimensional components of this Hodge locus, and the thing is that this is actually not a countable union. It's algebraic of those. This is ideally different from what happens for n equal to 2. Or for the case of the Wien variety. So, okay, so this is going to be direct by 3, myself, and very more. So this is the main part of the theorem. And actually, for n equal to 2, and t larger than 5, for t equal to 4, there are no exceptional components in the methodology focus. Actually, we can answer Voisin's question. Maybe we prove that the union of exceptional components and then T B is not asking. All right, so the picture is rather changing. We see that if we take more complicated hypersurfaces, actually hard structure will become more complicated. I will explain precisely in which sense. And then actually we get a much stronger result than the catalytic model. Look at this algebraic on the notes. All right, so this was basically the introduction. So now what I want to explain is how you can, yeah.
Does our conjecture imply that?
No. Good point. At least I don't know how. So it seems that the ideas come from a completely different direction. So Hodge loci as so and moduli people will be maybe more happy as an intersection problem. So analytic intersection result. Okay, so okay, so what I want to do now is maybe try to explain the heuristic guiding the proof of this theorem. Then the general result we get compared to the heuristic and what is expected, and then how to deduce that. Of course, I want that one to do the entire thing, but I will try to find it behind you. Question? Raise. All right, so as I said, main guiding idea is really forget anything about the geometry of families. Just focus on Hodge theory and see what we get.
So here, do you have any information about the distribution of the codimensions?
Yes, but it's not written yet. So we have some information. So for D minus 3, so if the codimension is smaller as possible, so D minus 3, there is a unique family, right? I mean, and the next one we also know it's D minus 7, and this is described geometrically also. And for the rest, it's and there are only finite units. But for the other ones, which are of larger dimension but still not general, we don't know exactly at which dimension it becomes infinite units of change. Actually, we should be able to really understand that closure. Okay, so let's start. So to explain the idea, I will try to recall kind of fast some Hodge theory. So suppose you have a polarized DHS on S. Well, remind you, this is a local system of the module of finite range, and then filtration on the associated holomorphic vector bundle span connection. And the important thing that I did not write down is Griffith transversality that I will recall in 1 second. So the fact is that such a get depth is given up by a Euclidean map, namely, which leads to the analytic form. So to describe the variation of a structure, you can actually completely forget about this local system and anything. It's just a certain map from the identification of S to a period domain that I will write as D mod gamma. So Here is the interior domain. And what are the properties? So first of all, and I will come back to that. So this is the C analytic manifold, and it is almost never algebraic. We'll come to the almost never one. Of course, if you are used just to considering families of Korean invited, you very well know, I mean, G gamma would just be AG and this is algebraic. But this is a super rare case because the invited, as I said, they are in weight one. But as soon as you will describe such structures which are more complicated, actually you will get a clear domain which is not algebraic, and this map is just complex analysis. So this is the first point that has to be explained. Second point is that it's super constrained in the sense that this is what is called horizontal. So I have to remind a bit about the construction of that thing, not too much because it will take forever, but still. So what is a Hodge structure? Suppose you have a polarized Hodge structure, just one vector space with a Hodge decomposition on it. Well, actually, associated to that, you can consider it's just given by a representation of C star in as the real white group with the underlying real vector space. Such a representation defines you exactly by graduation of DC, the sum of difficult such that difficult bar is equal to difficult. So from the point of view of group theories, it's quite simple. It's just such a representation. Okay? It is the same thing. Well, I forget it realize it is something like that. Now, if you are in this situation, what you can do is you can define the Mumford table that will completely encode the Hodge theory of that thing. And so this is, if you want to ask the closure of a Q. Of C star. So this is subgroup. It is a subgroup of the TNP. And if you want, this group compute the complexity of your Hodge structure. Because from another point of view, it's also the fixator of all Hodge tensors. Means a very big Hodge structure, which is B tensor A tensor B dual tensor B for all A. So the more Hodge classes you have, or the more Hodge tensors you have for your Hodge structure, the smaller it will become. Now, the basic fact is that because I'm assuming it is polarized, this group is actually reductive. So this looks a bit abstract, but this is actually really what we want to do. Now, if you have a variation, then at each point of S, you get the non-forking group at that point, or the Hodge structure at that point. Okay. And then basically the domain tells you that actually this is a local concentration of groups outside deciding the Hodge locus, where the group becomes smaller because there are some Hodge tensors of the theorem. Yes, minus dot locus. So this means that at all the points outside of this Hodge locus, basically there is only one group describing the structure, which is what is called the generic non-forking group. Or provide. Let me go into so this is the real. Now, what is T? Well, this is a complex analytic manifold that describe all Hodge structures on this Q vector space, so that the Mumford group is contained in T. All right, so in this picture, as I said, this domain found by the whole structure on fixed vector space VQ with no complete group containing G. So as a complex manifold, this is a homogeneous space, which is just a set of pure points of your relative group. Modulo is a stabilizer, and this stabilizer is a complex. So the situation is not close to what you know for single space when you uniformize the Abelian bodies. Except in single space, a major difference is that this group is maximal compact. Okay. So this makes it a Hermitian symmetric domain, and then the quotients will be algebraic. But in general, this guy is not maximal compact, and so the quotient would just be complex and native. So what are the features of this thing? Well, it keeps track of Hodge theory in the following sense. If you look at the tangent bundle B, at each point, this tangent bundle is a quotient of the Lie algebra complexified of G. And on this Lie algebra complexified, there is an action of G, and so it is also a Hodge structure. So it means that the standard space actually has a non-trivial expression, which is it looks like this. Okay. It has a decreasing integration coming from the Hodge equation on the Lie algebra of the group at each point. So, and what is the constraint of horizontality? Horizontality can be that actually this field has to satisfy a very complicated PDE, namely it has to satisfy the fact that its derivative maps the tangent space of S inside the smallest piece of the distribution. Of course, this distribution is completely non-integrable. So this is super constrained geometrically from a differential geometric point of view. Questions about that? So again, in the very simple case of Ziegler space, because the weight is 1, actually this state is the full k is equal to 1, and the tangent space is the original tangent space. So you never see this constant. Okay, and all right, so gamma in this definition is essentially TOC. That would be cool. And so the quotient becomes a half-length manifold, usually not compact. So what is the already in that description? What is the most important numerical invariant of a Hodge structure? This guy, this K. Okay. So I will call this the level. So this is the largest K, such that F minus K TP is different from F. Of course, it's filtration running F minus infinity and decreasing. This is the first integer where it's stabilized. And if you prefer, it's also as the largest K, such that if you look at the Lie algebra as a Hodge structure, I'm asking that of weight 0, so all the pieces are the form G, K minus K. And I'm asking this is the largest case of that E minus KK from 0. Okay. And the remark is that this invariant is more precise than the weight. It's always smaller or equal to the weight variation. So, it's more precise. For instance, everybody in this room knows that the moduli of K3 it's essentially constructed out of a Shimmer variety. So exactly the PL domain here. It's also the quotient of gamma is also algebraic, which is surprising because as I told you, it's all essentially only if it comes from weight 1. But actually for K3, the level is 1, although the weight is 2. And this is well known, and this is you guys take a construction to out of the K3 concept of universality. So, and so the fact, let me write the fact, is that T of gamma as an economic function at this level 1 with 2 power. Okay, so now what is the main picture? Let me maybe now the picture. So what is the relation of this picture with other light? Now that I can do this, well, just the following. I get this to the map. Right, and now I want to describe the possible locus. That. So how do you do that? Well, it's very simple. Saying that you are in the hot locus, it just means that your matrix magnitude becomes smaller. So this means that inside the T mod gamma, you will lie in some T prime mod gamma prime, which has exactly the same shape, but it's much smaller. So actually, you have a countable union, and this will justify the countability of the catalytic method. So this is a countable union for all T5 sub H of GT. And this is countable because all those groups are kind of fused. So we have this locus, so we have this complex manifold. Inside this complex manifold, you have this countable union of complex submanifolds. And now with this Hodge locus, well, there's a fiber. The pre-image of this countable union by this complex analytic map. Okay, so this is the main diagram of the entire story, because basically it explains all the problems and all the solutions. So this means that a special stability, so C is like S, a special stability, in the sense of being one of these irreducible components described by catalytic Capron, is the same thing as saying that C can be written as pi minus 1 of some pi mod gamma pi, and then you have to take a irreducible component. So now this is super surprising, right? This guy is complex analytic. This map is complex analytic. I'm taking the pre-image in something quite objective. So a priori, I could get infinitely many connected components of a very complicated complex analytic manifold. So catalytic Capron is telling you that no, this is undivided. Okay. So all this is not but this is one of the main progress. I think you could give some more conceptual explanation, also technically speaking, the book very similar to catalytic Capron. I guess then people do a lot about thickness and speak. So the way we see this is the point theorem. To Ben, myself, and Jacob, says that actually, although this map is complex analytic, topologically speaking, it looks like an algebraic map. Maybe it's topologically big. So in technical terms, in community structure with RNA. So basically, what it tells you is that actually you can find a finite atlas of this complex manifold by real analytic, real algebraic charts, such that in restriction and here I will take also a finite atlas, so that if you write this map in those charts, actually you need only complex analytic functions restricted to complex and the real expansion function. And then this implies calculating the of results using what is called polynomial. So the closing starting for. So how do you prove CPK? Well, you take this D prime and gamma prime. You have to prove that for the RNX structure of D mod gamma, this is definable. So this is taken that structure. So you take the pre-image and the phi, which is a tape map. So this is a tape subset of Si. But it is also complex analytic, and now you have a version of tau for only structure that takes that tape subset. So the tape subset, which is complex analytic, is actually algebraic. All right, so at that level, we are back to the approach. So now let's do more. You see, as I said, that the locus from that point of view has to be understood as an intersection. This is the intersection of the image of phi by this complex analytic map with this countable unity. But if you have an intersection, the first thing to do is to look whether your intersection is typical or atypical. The definition is the following. I would say that the spatial stability atypical if it has not the expected codimension. So if the codimension of its image in D mod gamma inside T mod gamma is strictly smaller than what it should be, and what it should be is just the sum of the codimension of D prime mod gamma prime. Right, the codimension of the phi at this time. And otherwise, I say it is typical. Okay. Good. Now, if there is a logic in life, then atypicality should be rare, then typicality should be a common. So this is a heuristic. Conjecture. In 17, and it was defined this value more in our paper. And if you want, this comes also this is a derivation of conjecture by King and Pinker for Chinois variety. This is the development conjecture beyond this. And it says the following is that, well, other than looking at the locus, I can decompose it into two pieces, the union of the atypical components, that will be in this way, and the conjecture is that this thing can be algebraic. I think that should be very clear. That's it. And the second part is that if I take the typical locus, then the guy has two choices, either it's empty. If it is not empty, it is dead. Or unempty dead. So I will not give, there are a lot of examples of this conjecture. A very special case, for instance, is the following version of the umbrella conjecture. Suppose you have a variation of a structure, and suppose that S contains a Zariski dense set of CM points for this variation. Then it implies, just this conjecture implies that actually the period domain should be a Chinois variety and that the period map should be dominant. So essentially, this situation can happen only for Chinois varieties. Right. So from now on, let me now state results. So from now on, I would assume that the joint morphic group, it's semi-simple part, so it's a joint group is simple. My assumption from now on, it makes the statement of results much simpler. So this is the case, for instance, for family of smooth cycle space. Okay, so the main result that we have in direction of those conjectures is geometric version. Okay. So basically, our main problem are the atypical points. This is the only open question. So it says that actually, if you look at the atypical locus of positive dimension, then it is very one. So we don't know for the points. We would like to prove that there are only finite and many atypical points, but that we don't know. Then what about the typical locus? Well, not yet. So now this is nice, but then we would like a nice criterion to know when the locus is actually atypical. And the theorem is that suppose that the level is at least 3, then this implies that actually the other locus is clearly. In particular, the corollary of this is that the level the B larger than 3, then is equal to the other locus of positive dimension, which is more atypical, and so this is the one. Yeah. So you see that really the dichotomy is between the small level, so for family billion varieties, or maybe in level 2, then you could have some typical locus, which is extremely dense, and but otherwise, as soon as the level is at least 3, actually everything is atypical. And so, in particular, because of the first part, the positive part is algebraic. Now, the theorem 4. So, what about the typical case? So, in level 1 and 2, we prove that the Hodge locus S the typical reality. So, in particular, the level is 1 or 2. Then it is dense. Actually, we would like to prove it is dense, but there are still the atypical points that the Hodge locus, the Hodge locus. So this explains the particular case for the family varieties or for the non-reference locus. And actually, this was improved by recently by 25 organizations. So for the same time, maybe I will not write that soon because I'm almost late already. Basically, it tells you that as soon as there is a numerical reason for this thing to be non-empty, and as soon as there is a T prime and gamma prime whose dimension plus the dimension of the image of phi is larger than the dimension of the ambient space, then actually this sort of locus is not empty in level 1 or 2. Okay. For instance, it's proved in AG that any subvariety of AG of dimension at least G, dimension, of course, dimension at least G, the Hodge locus is dense. For instance, the Taurian. I heard a bit, so I'm super late. So these are the results. Now, how do you prove this? Let me just say a few words. Maybe Ben will come back to functional transcendence, I'm sure. But there are two tools. The first one I already bought is this omnium business that tells you that the labs are taped. And the second part, which in some sense is completely different from another word, is functional transcendence results, which is developing conjecture and actionable type conjectures or results. And basically, let me just say in a few words what you have. So you have a situation where you're receiving that. But written there is this universal couple of the gamma. And here there is some complexity. So this guy I wrote it as a homogeneous space, Well, actually, it's open in this half back dual, which is some buffer fragment for each check. So you have two economic variances, each check and S. And the functional constant that you want to study are basically the comparison between this network structure and that one through the map, or if you want to, the universal map. And of course, they have nothing to do together. The functional constant tells you that actually there is a way of precisely comparing the algebra structure here. Okay, I don't want to speak whatever, so I just take